In this lesson, we are gonna focus on center of mass. So before we begin, what is center of mass? The center of mass is the point through which or the point at which the mass can be considered to be concentrated. What do we mean by that? For example, if I have a uniform ruler over here, its mass is gonna be at the center of it. So its center of mass will be at the center of the object. It would mean that the weight around it is equal in all directions. So in every direction from it, the weight will be equal. So on the left and right, there will be equal mass. On the top and bottom, there will be equal mass from the center of mass. Now in our examinations, the most basic questions we might get are about finding the center of mass given some masses. So consider the same ruler over here, or we can consider this to be weightless now, and we are gonna attach particles on it. So we can attach a mass over here, let's say it's 5 kgs, another mass over here, let's say it's 2 kg, and another mass of 3 kg. Now we might be asked to find the center of mass of all of the particles given the distances. So this can be considered to be 19 meters. This is 3 meters. Now we are asked to find how far the center of mass is from point A. In this case, to find the center of mass, we have to use a moment. The downward force we have is 5g from here, 2g from here, and 3g from here. The upward force and downward force must be equal, so 5, 6, 7, 8, 9, 10. So there must, on the center of mass, we must give a 10 joule force upward. So we can consider moments about any point. We can do it about A. In this case, clockwise moment will be equal to anti-clockwise moment. The weights give a clockwise moment, while this gives an anti-clockwise moment. So we'll have 19 times 2g plus 19 plus 3. So this distance over here is 19 plus 3, or 22 times 3g. This will be equal to 10g times the distance. So this distance over here is the distance of the center of mass from point A. So we can find that from here we'll have 19 times 2g plus 22 into 3g by 10g. X will have a value of 10.4. Now a better way to organize this would be to use a table. So on the table we write down the masses and the distance from the point we want to find out. In this case we wanted the distance from A, so we'll write down distance from A over here. Now for the first mass, this was 5 and the distance was 0. For the second mass, the mass was 2 and the distance was 19, and for the third mass, the mass was 3 and the distance was 22. Now we'll draw a double line, and on the right it's for the final or total. So the total mass will be 5 plus 2 plus 3, which is 10, and this will be the center of mass the distance of the center of mass from point A. So in the same method we can solve this. We'll multiply this with this, this with this, this with this. So 5 into 0 plus 2 into 19 plus 3 into 22 is 10 into x bar. We'll get the same value of 10.4. Now this is in one dimension. What would we do if there were two? So if I have a graph over here, this is y, this is x. Now we can be given some masses over here. So for example, there's a mass at 0,5, another mass at 2,3, and another mass over here at 1, minus 2. So now we have to find x bar, so the x coordinate of the center of mass, and y bar, the y coordinate of the center of mass. So from here we'll draw a table. Must be given the masses at each point. So if we're given this is 4 kg, this is 3 kg, this is 10 kg, we'll write down the masses. So we can consider this to be A, this is B, and this is C. So A, B, and C. If we add them together, we'll get the total. We'll have masses, the x value and the y value. So for mass A, the mass was 4 kg, the x coordinate is 0, the y coordinate is 5. For B, the mass is 3 kg, the x coordinate is 2, the y coordinate is 3. For C, the mass is 10 kg, the x value is 1, the y value is minus 2. From here we know the total mass will be 10 plus 4 plus 3, which is 17, and we'll have x bar and y bar. Now we'll solve two equations to find x bar and y bar. So we'll multiply these together and sum them together to get the product of this. So 4 times 0 plus 3 times 2 plus 10 times 1 is equal to 17 x bar. X bar comes out to be 16 by 17. Now for y bar, we'll have to do the same, but instead of the x coordinate, we have to do it with the y coordinate. So the mass times the y coordinate, and we have to sum that. So we'll get 4 times 5 plus 3 times 3 plus 10 times minus 2 is equal to 17 y bar. Y bar comes out to be, here y bar comes out to be 9 by 17. Now instead of just being separate particles at different points, we can also have something like a paper. So in this case we call them lamina. Lamina are very thin 2D shapes which have length and breadth, but their height is negligible. So a piece of paper can be considered to be a lamina. So a paper like this will be a rectangular lamina. Now we have to learn the center of masses for some different types of lamina. For a rectangular lamina, so one like paper, so something like this, the center of mass would be at the point where the two diagonals join. So this is the center of mass. We can represent it with the G. If we are given these points, so x1, y1, the next point x2, y2, the next point x3 y3, and the fourth point x4 y4. We could just take the average x and y values to find the center of mass, or we can find the two equations for the diagonals and find where they intersect. Up next we have a circle or a circular lamina. This will have a center of mass at the center of the circle. So this is the center of mass. Next up we have triangular lamina. So we are given a triangle, we are given points A, B, C, we are given the coordinates x1, y1, x2, y2, x3, y3. So for a triangle, the center of mass, or G, will have a coordinate like this. So in this form, x1 plus x2 plus x3 divided by 3, comma y1 plus y2 plus y3 divided by 3. We also have to remember it for sectors and semicircles. So for a sector, the center of gravity will fall on this line, and we have to find this value over here, which is x bar. X bar over here would be twice the radius of the sector, and we'll also need the angle alpha. So this is the angle alpha. So if we use that, we'll get a formula of 2r sine alpha divided by 3 alpha. We must use it in radians. Finally, we can take out the case for a semicircle from here. It doesn't have to be a separate point. Semicircle is basically a sector where the value of alpha is 90 degree or pi by 2. So x bar will be 2r times sine pi by 2 divided by 3 times pi by 2. So the value of x bar will come out to be 4r by 3 pi. Now we can have a composite lamina. So a composite lamina is built up of different shapes. So we can have something like this, or we can have a triangle attached to a rectangle. So this is the rectangle and a triangle is attached to it. We might have to find the center of gravity of this shape over here. In this case, we'll use the table again. Instead of masses, we'll have the ratio of masses. It will depend on the weight per area of the paper. We'll have x and y. The ratio of masses will be equal to the ratio of area. So for the rectangle, this is length into breadth. The breadth is the diameter. Oh, my bad. So this is b again. From here we can just find the coordinates of these 3 points of the triangle and find something for it. we must be given the height over here. This will be half into b into h. So now we'll have a total over here. The total will be length into breadth plus half into breadth into height. The x coordinate for the rectangle would be L by 2. For y coordinate, this would be b by 2. And for the triangle, the y coordinate will again be b by 2. I'm considering this point as the origin over here. This point over here will be L comma b by 2, and this point over here will be L plus h comma b by 2. The other vertices of the triangle will be L comma 0 and L comma b. The x coordinate of the center will be L plus h divided by 3, and the y coordinate will be b plus 0 plus b by 2 divided by 3. Now we can write this composite lamina as the addition of two shapes. In other cases, we might have the subtraction of shapes. So we might have a square over here, and we can take away a sector or a circle or another rectangle from here. So you remove that and we get a shape like this. So in this case, we'll apply the same things. So we have to find the area of the large one and the smaller one. So we can have ratio of masses. The difference with this would be, in this case, we multiplied the ratio of mass with the x coordinate and the y coordinate over here, and then we added it. So we had a case like this and this. In this case, we added the two terms. However, now if we have a subtraction over here, we'll have to subtract that. So if we are given this shape, we are told that this is 3, this is 4, this is 4 again, and this is 6. So the larger rectangle is 9 times 8. So it has a length of 9, a breadth of 8. It has an area of 72. The smaller one has an area of 4 into 3, which is 12. So the total area of the whole shape will be 72 minus 12, which is 60. Now for the x coordinates, the center of mass of this shape will be 6. This is 9, so the whole over here is 9, so halfway through it, so 4.5, and the total height is 8 meters, so we'll go halfway through it, so 4 meters over here. So the x coordinate of the center of mass of the larger rectangle is 4.5, and the y coordinate of that is 4. Now for the smaller one has a center of mass over here, so over here. Now this distance was already 6, and this distance will be half of 3, so 1.5. So the total distance will be 6 plus 1.5. This will be 7.5. And for the y coordinate, this part was already 4, and this part will be 2, so 4 plus 2 will be 6. And we have x bar, y bar over here. To find that, we'll do 72 into 4.5 minus 12 into 7.5 is equal to 60 x bar. We can find the value of x from here, and for y we'll do 72 times 4 minus 12 times 6 is equal to 60 y bar. We can find the value of y bar from here, so we get x bar from here and y bar from here. We can also have cases of folding. So in this topic, instead of thinking of folding as folding, we'll think of adding a different so if I have a paper and I fold it in half, I'll add something over here. So I'm gonna fold it like this. So I'm gonna fold the top into the bottom. So the density of the bottom part increases. We have an additional part in the bottom. This will be added, and we lose the part in the top, so that will be subtracted. So if this was 2 units by 1 unit, so this is 1, this is 1, this will be 1:1, this will be 1:1. Now if I want the ratio of masses, we'll get 2 plus 1 minus 1. The total will be 2. The x coordinate of the center of mass will be 0.5, 0.5, 0.5. That won't change. For the y coordinate, initially for the larger shape it is 1. For this second one it's 0.5. For the third one, this is already 1 and this is 0.5, so this is 1.5. So all the x coordinates are the same, so this will be 0.5 anyways. Now to find a y bar, we'll have 2 into 1 plus 1 into 0.5 minus 1 into 1.5 is 2 y bar. From here we can find y bar. Now we'll also be asked question about toppling. So if I have an inclined plane and a lamina on top of it with its center of gravity over here, if its center of gravity passes like this, or at max in a scenario like this where the weight passes through the edge of this, so like the weight passing through this point, this point is the limiting equilibrium. If I tilt it any further, the lamina will fall because it won't have a support under it. So if I get more steep, this line goes through this part. So the line doesn't go through the contact of the lamina and the surface. Since the weight acts outside the surface of contact, this will topple. So not in equilibrium. We learnt about lamina, which are 2D shapes like paper, which are thin and has length and breadth only. We'll also have to calculate for framework. So framework can basically be thought of as wires or strings. So if I have a rectangle, so this is A, B, C and D. AB is a string, BC is another string, CD is another string, and AD is another string or where. For framework, we'll make the tables like this. So mass, and on top we'll add all the wires. So the wires are AB plus BC plus CD plus DA. By doing that, we get the total. So in cases like this, we'll be told that the ratio of masses are the same, so it will just depend on the length, or we might be told that AB has a weight of 3 kg, BC has a weight of 2 kg, something like that. Most likely we are gonna be given the dimensions. So this is 10, this is 7, just for example. So now the mass ratio will be equal to the ratio of length. So AB has 10, BC has 7, CD will again have 10, DA will again have 7. The total will be 7, 10 plus 7 plus 10 plus 7, which is 34. This is the total mass. Now the x coordinate, or the x coordinate of the center of mass of where AB will be at x equals to 5. For BC it will be at x equals to 10. I am considering D as the origin. For CD the x coordinate will again be 5, and for AD the x coordinate will be 0. Now about the y coordinate, AB will have a y coordinate of 7, BC will have a length of 7 divided by 2, so 3.5. CD has y bar of 0, and AD has a y bar of 3.5 again. This is x bar, this is y bar. Now we can find x bar and y bar. So 10 into 5 plus 7 into 10 plus 10 into 5 plus 7 into 0 will be equal to 34 x bar. We can find x bar from here, and we can find y bar like this as well. So 10 into 7 plus 7 into 3.5 plus 10 into 0 plus 7 into 3.5 will be 34 y bar. Now in any case, if a lamina or a framework is hanged from a point, so if I have this shape with the points A, B, C, D, E, F, and I'm told that B is taken as the fixed point, so we are hanging it through B, and the center of gravity will be somewhere over here. Now if this happens, the shape will rotate in such a way that the center of gravity lines up with B. So the center of gravity, or the shape will rotate something like this. So I'll do it in red. And if that happens, the center of gravity will fall just under B. So this will be stable. If it was not in this position, there would be a resultant moment on it, causing it to come to this position. And this is enough for center of mass calculations in mechanics, especially Edexcel M2.